Let's continue with capacitor labeling. In the previous slide right here, we discussed that if we have a decimal to the right of a number to the right of the decimal, we read that as a microfarads. And then electrolytic, we say that if MF means microfarads as well. For this one right here, this is a different type of labeling the capacitors. In this case, if we don't see a decimal point, we just see the value, it will mean the first two digits, and then the third digit will be the power. So let's see what it says here. A label such as 103 or 104 is read as 10, the first two digits, and then the third digit is the power of which the 10 is raised to. So it will be 10,000 picofarads. So it will mean the value, but the unit will be picofarads. Like 104 will be 10 to the 4, it will be 100,000 picofarads. So it will be the multiplier, the unit will be the picofarads. Where the values are marked as 330 or 680, the units are picofarads as well. So like I said here, that is not a standard way that I can show you, okay, this is that's what it means, or there is a table. There are several different tables for capacitor readings, okay? So you have to be, when you buy it, there is going to come with a table, so you can just follow that that reading, so you know what the value of the capacitors are. So right here it says, what is the value of each capacitors? So right here, you see I have, this is the first way it's reading it. So I have 22 times 10 to the 2, so it's going to be 2,200, and the unit is picofarad, and right here the whole number is spelled out. So these two capacitors actually are the same value. Okay, so we have enough of capacitors and a little bit of the background and how to read and how to select them and what they are. Now let's see how we analyze them once they are in a circuit. Capacitors can be and are always part of circuits. Throughout chapter 6, we learned different techniques of how to analyze and solve electric circuits by resistors only. So resistive electric circuits were what we learned. However, once we move into the real design world, we are going to realize that most of the equipment that we are going to use can be modeled as resistive, capacitive, and inductors. And what we use is not DC circuit. What we use in our house are AC circuits, okay? So it is important that we understand how to deal with capacitors. We are only learn how to add them in both parallel and series circuits, but later, once you take the AC component of this class, you're going to learn about the constant rates, how fast they charge, how fast they discharge, their characteristic equations, how they behave, how they are depending on frequencies. But right now, for us, we are going to learn the basics, prepare you for AC currents in the AC second part of this class. So series capacitors, when capacitors are connected in series, the total capacitance is smaller than the smallest one. The general equation for capacitors in series is, so capacitors, when they are in series, they add up like resistors in parallel. So we add the total capacitance is follow the same rule. If it is a pure series connection capacitors, the smaller value of the capacitor is going to be the limiting factor of the whole circuit, which means that your total capacitance will be smaller than the smaller capacitor in the circuit. The total capacitance is going to be the reciprocal sum of the reciprocals of the capacitors. Just like the question says here, total capacitance is 1 over C1 all the way to Cn. The total capacity of two capacitors is the same, it's just for two ones, right? And again, if you solve this, if you solve these two, which is totally doable, you'll realize that this equation, it is the same equation as when you have resistors, two resistors in parallel. So it's going to be the product divided by the sum of the two capacitors, okay? So then let's move to series capacitors. I have a 0.01 microfarad capacitor is connected in series with an 800 picofarad capacitors. The total capacitance is, so they are in series, so it's going to be this value times that value divided by the sum of the two values. So here I have 1, 2, 3. So I have 1 picofarads times 800 picofarads, so that will be 800 picofarads. So it will be 800 picofarads divided by 801. So let me see what I get here. Okay, so the answer that they are getting is 444 picofarads. So if I do 1 divided by, if I take this into the picofarads, I will get 1 pico multiplied by 800. So it would be, so 1 times 800 and then multiply the pico, so it will be, pico is 12 plus 12 is 24, and then divided by 800 divided by 12. So you get 444 picofarads. Now how to do parallel capacitors. When capacitors are connected in parallel, the total capacitance is the sum of the individual capacitors. The general equation for the capacitor in parallel is, so the total capacitance once they are connected in parallel is just their summation, algebraically summation of each individual capacitance, is backwards to when we have resistors, right? Capacitors in parallel add up like resistors in series. So that's very interesting how that happens. Then they give us an example. So we have here, we have 800 pico, and then we have 0.01 micro. So we say 0.001. So we get that we have 1,000. We just add them up. If I 0.001 microfarad capacitor is connected in parallel with 800 picofarad capacitor, the total resistance is. So you see how drastic the difference is. If they are in parallel, they add up, but if they are in series, it actually halftens. So that's how the capacitors are added, and that's as much as we are going to learn about the capacitors, okay?